All right, so welcome back. Let us move on to the next topic. See, so today basically we are going to start a new subdomain. But before moving on to that, I would really want you to look at some images and try to answer yourself what are these images representing. All right, have a look. Look at this image, look at this, and then look at this. Try to answer this question. What do you see in these images? I would say that it's a painted wall and paint is peeling off from the wall. It's a plant root trying to move inside the concrete. It's a rusted car. It's a pothole. It's a statue probably made up of some stone, and I can see wear and tear over the statues. Fine spots eating up of the statue. It has been eaten up. So if I were to summarize what's all happening in these images, I would just write this. Weathering. So that's what is the topic for today's lecture. Weathering. What do you understand by weathering? That is my first question. So as we move, I would really like to emphasize on this question. What is weathering? So as we are all aware of the topography of the earth, it's not a flat surface. We have mountains, we have hills, we have plateaus, we have flat terrains, and then we have deep ocean basins, then we have volcanic arcs and all that. It's not a flat terrain. It's never a flat terrain. All right. There are peaks, there are depressions. What happens is that material is being eaten up from these heights. They are continuously being eaten up. And some material is generated over here. This generated material is then plugged up and set in motion. After that, they are moved by various agents. That is, they are being transported. And after transportation, they are basically deposited in this basin and deposition takes place. Once the deposition occurs, they with time gradually get cemented and by the process of diagenesis convert into what is known as sedimentary rocks. So this journey is all about geomorphology and sedimentology. In entire course, we will be studying various aspects that are occurring in this journey. So for the sake of today's lecture, we are going to concentrate on this eating up. So this disintegration, this breaking up of material is what is known as weathering. So if someone asks you what is the source of sedimentary rocks, one word answer would be weathering. Weathering is the source of this sedimentary rocks. The source material is this. So whatsoever be the material of these hills and mountains or this crustal material, they are being broken into pieces via various different processes and they are generating some material. This material is now being transported. So here we will talk about hill slopes. After that, in the process of transportation, we will basically talk about fluid dynamics. Then we'll look transporting agents of river, wind, glaciers, and then we'll talk about lakes. Then we'll talk about this transition zone, that is deltas and estuaries. Then we'll move on to marine realm, shallow marine and deep marine. So this is going to be the journey. But today's lecture will be focusing on this, only this zone. What is happening in this zone? That is weathering. All right. So the source for sedimentary rocks is weathering. Now, let me define what is weathering. So weathering, when we define, we say that it is the physical disintegration, it is the chemical or biochemical decomposition of a rock or a crustal material. All right. So this is how we define weathering. It's taking place over some elevated areas, and they are basically generating some sort of material of various sizes or various grades. All right. So this material that is being generated out of weathering via these processes, we will deal with each and every word of this, don't worry. So basically, the material that is being generated is known as clast. Adjective would be clastic. The material that is generated is known as detritus. It is also known as terrigenous because it is derived from land. Since most of the weathering is confined to the surface and to this crust, and this crust is majority wise composed of silicates. So these silicates are what is being generated. Therefore, it is also known as siliciclastic material. This material that is being generated. So these are the words which we will witness in geomorph and sedimentology again and again. So they are synonyms, just the synonyms. These are the source material of sedimentary rocks being generated. All right. So in weathering, I have told you that we have got physical disintegration, mechanical or physical is in itself is known as mechanical. This is chemical or mineral. Chemical or biochemical. Chemical or biochemical. Yeah. Biochemical. So what is happening in physical weathering? See, say for example, I've got a cube. Its dimension is 1 meter, 1 by 1 by 1. I ask you to calculate the total surface area. It is going to be 6 square, 6 meters square. After this physical weathering, that is the physical disintegration. Let us say, for example, we have generated 8 cubes, total 8 cubes, each of 0.2 meters. All right. So the total surface area of this one cube, it is going to 6 into a square, 0.2 square, 0.4. So the 24 meters square. Of total 8 cubes, 8 into 0.24. Let us make it 5, huh? Because it is not serving the process. So let us make it 5. 0.5 meters. 5 5 are 25. 25 6 are 1.5 meter square. 8 into 1.5, 12 meter square. So the surface area is doubled. So this is what physical weathering does. It increases the surface area. Say for example, prior to weathering, I had only this much of area available for weathering. Weathering occurring only at this much of area. So if I try to, unfold all these cubes, then the area has significantly increased, almost doubled. So this is what physical weathering does. Whereas what does chemical weathering does is it also increases area, but primarily it changes the chemical and mineral composition of the rock. Whereas physical weathering occurs without any change in chemical or mineralogical composition. That is the primary difference. All right. So now you tell me, is there a difference between chemical and mineral change or mineralogical change? Is there any difference between the two? This is feldspar. This is a clay mineral kaolinite. So in weathering, generally feldspar changes to kaolinite. What happens is this K plus is replaced by this aluminum. Loss of K plus. This is known as chemical change. Chemical change. All right. But what is this mineralogical change? Say for example, this block was made up of granite. Granite. What is the composition of granite? Granite is generally feldspars, quartz, and what else? Mica. All right. So in this granite, after weathering, what is happening? Feldspars have changed into kaolinite. Kaolinite plus quartz plus mica. This from feldspars to kaolinite. So this feldspar to kaolinite, this mineral change, this is known as mineralogical change. So that is why we write chemical and mineralogical changes. But there is a difference between them. Chemical means what? The ions that is making up of a mineral, they are changing. They are being substituted by one another. Mineralogical change, the entire mineral is being replaced by some another. A new mineral is forming. A clay mineral is introduced. Feldspars are lost. All right. So I hope this is clear till now. Now we are in a comfortable position to define basically what do we mean by weathering. So finally, I can answer this question. What is weathering? All right. So to answer this, I would write it is the physical disintegration chemical and biochemical decomposition of a rock to generate siliciclastic at, now this is the good part, at, see, if this is my surface, so weathering is generally occurring sub-area, that is between these two layers, between atmosphere and lithosphere. So good authors always use the word at the interface between atmosphere and lithosphere. If I were to write this in an easier language, I would have said at or near the surface. So now we have defined weathering, and comfortably and very comfortably we have talked about each and every. We have basically weathered the definition of weathering. All right. So one more thing I would like your attention on this. See, we have seen that weathering, very important, you need to mark this down, is an in situ process. In situ process that is happening there itself. No motion involved. All right. But once the material is weathered, I have got the clasp. Now this will be plucked out by the process of erosion. That is plucking and set in motion. What all are the agents of erosion? We have rivers, we have glaciers, we have wind, and we have sediment gravity flows. Sediment gravity flows. After that, once set in motion, they are carried forward and transported to the destinations. Transportation, long-term motion. Now they are set in motion by the process of solution, suspension, saltation, rolling, sliding, and then they are deposited. So what he says is that if I add all these three, 1 plus 2 plus 3, together they are known as, together the process is known as denudation. Denudation. Very important. It has been asked in multiple exams including GATE and GSI. Denudation. Denudation is a combination of weathering, erosion and transportation. All the three are involved. All right. So we are successfully done with what? Now let us move on to why. Why does weathering happen? Tell me. Next question is why. So I'll explain you 2-3 reasons. But before that, I'll always use this analogy. Say for example, we have got a ball over here, and this is at a height of h. Obviously, this will have a high potential energy, and this will have a low potential energy. So the ball has a tendency to move from high potential energy to low potential energy. Why? Because it will be more stable over here, isn't it? So this is what is happening in thermodynamics. Thermodynamics. Please be patient. Listen to this for a few minutes. Things will be very clear. Thermodynamics talks about whether the reaction will occur or not. Will occur or not. It talks about whether the products are more stable than the reactants. If yes, if the answer to both these questions is yes, then we say that reaction is thermodynamically feasible. Very simple, very simple. Every reaction occurs because it has a tendency to move from this higher energy to this lower energy, from higher potential energy to a lower potential energy. Just in the case of reaction, in talking in terms of thermodynamics, we say that a reaction occurred and hence there is a release of Gibbs free energy, negative Gibbs free energy. Gibbs free energy. Gibbs free energy. And it is thermodynamically stable. The reaction is thermodynamically stable. Higher potential to lower potential. Similarly, from this reactant to this product, a lot of Gibbs energy is released because every reactant wants to attain a stable position. Why am I talking about this? It will be more clear in the upcoming few minutes. All right. So this is about thermodynamics. It will tell you whether a reaction is bound to happen or not, whether a reaction will occur, whether weathering will take place or not. Why? Because weathering is what? It is just a combination of reactions. So are they reactions prone to happen or not? This will be decided by what? Thermodynamics. And why? What are the factors that will govern whether the reaction is going to happen or not? We will just see those conditions. But before that, let me talk you through those conditions first. See, say for example, this is my surface. This is my surface. All right. As I increase the depth, the pressure and temperature, as I move down, all the three increases. You are aware of the situations that at greater depths, igneous rocks are generated. Igneous rocks are generated. At somewhat shallower depths, metamorphic rocks are generated. At even shallower depths, but at depth, sedimentary rocks are generated. None of the rocks are forming at the surface. You might be confused about this, that sedimentary rocks are forming at surface, but actually no. They are forming in ocean basins. They are deep. And that too, when we have sufficient layers of sediment, they get buried. They witness an increase in depth, temperature, pressure, compaction happens, diagenesis happens. They are all occurring at certain depth, certain temperature and pressure conditions. So they're not forming at the surface. They cannot form at the surface. They require those calm and conditions of those depth. So they are forming over at certain depth. All right. Say for example, pressure is 500 MPa, temperature is 2400 degrees Celsius, depth is 700 kilometers. All right. Now, via the process of exhumation or tectonic uplift, these rocks will be brought onto the surface. So I will have a scenario where I'll have this igneous rock over here. I'll have this metamorphic rock over here. Don't be bothered about the sequence. I'm just giving you an example. All right, the sequence can be any. All right. So these igneous rocks, they all the three set of rocks are now brought to the surface. Now you tell me. Have a close look. This igneous rock has moved from this depth to this. This is the edge. The constituents, the minerals, the crystals of these igneous rocks are more stable at these pressure, temperature, and depth. But on the surface, temperature is approximately 10 degrees Celsius. Depth is 0 kilometers. Pressure is 1 atmosphere. Will they be stable over here? No, highly unstable. So I have now generated a scenario like that ball example. They are at a very unstable position. They tend to move to a stable position. I have increased the height and brought them to a very unstable position. So now they tend to move towards a stable position. That is why this reaction is thermodynamically feasible, because of this stability. Now there will be a lot of Gibbs energy released. What do I mean by Gibbs energy? See, for example, if igneous rock is traveling from this to this height, all right, negative Gibbs energy is released. If it is moving from this height to this height, now say for example it is moving from this height to this height, somewhat less Gibbs energy is released. From this height to this height, somewhat less Gibbs energy, because it is traveling a lot of distance. Greater the distance it is traveling, more is the Gibbs free energy releasing. Why? Because it is coming from a depth. Say for example, they have to come at this depth. If it is coming from 100 kilometers below, it has to travel a lot of distance, and the conditions at 100 and 0 are very different from each other. But the conditions from 50 to 0 are not that different. Conditions from 10 to 0 are not that different. So a reaction, if taking place in this interval, it will release somewhat Gibbs energy. This will release more Gibbs energy. That is, this reaction is more feasible. This is somewhat less. This is even less. So this is what I meant by thermodynamic stability or thermodynamic feasibility. So most of the rocks are formed at subsurface, below the surface. Therefore, when brought onto the surface, they are very, very unstable, and hence they try to form into some new crystal structures, into new minerals that are stable at those pressure, temperature, and depth conditions. All right. Another reason I will give you. So in these depth, now if I do not remove this diagram, and if I say at this depth, olivine forms, and here quartz forms. All right. Now both olivine and quartz are brought onto the surface. Both olivine and quartz are brought onto the surface. You tell me which is going to be the more unstable form, olivine or quartz. Olivine is forming at this depth, so it is going to be more stable over here, and as soon as I bring it to the surface, it will be very unstable and it will start dissolving. So at surface, this olivine is highly unstable, and this quartz is very stable. Why? Because it has formed on a very shallow depth, very surface-like conditions. So this formation, this crystallization is defined by Bowen reaction series. Reaction series. Contrary to this reaction series is the Goldick reaction series. Goldick dissolution series actually. Dissolution series. What it says is that if I'm talking about dissolution or dissolution, so olivine is going to dissolve first and last is quartz. Remember, olivine is forming first as per the Bowen reaction series, but it is going to dissolve first because it is highly unstable. And this quartz is highly stable or very resistant to weathering. So I've given you two reasons. One is the temperature, pressure, depth conditions. Another is this, which is one and the same. Third reason is that, see, we are talking of siliciclastic material. That is mostly alumina silicates. These are all silicates made up of SiO4 tetrahedrons. So these SiO4 tetrahedron in mineralogy, you will see that they are either single in nature, or they can exist in pairs, or they can exist in chains, or in sheets, or in 3D frameworks. 3D framework. This is what is known as degree of polymerization. Degree of polymerization. Existing single, it means we have a lower degree of polymerization. Example is olivine. If it is existing like this, it means it has a higher degree of polymerization. Example is quartz. Now you only tell me, if I want to dissociate, if I want to disintegrate something, a single compound is easy or a mesh of 3D network is easy for me to disintegrate? Obviously, this is going to be easy. That is why olivine weathers easily. Weathers easily. And it is very difficult to weather quartz. That is why we call it as a resistant mineral. Resistant to weathering. This is the third reason. From the structure. Alright. So first is thermodynamics, and the second thing that decides is kinetics. Kinetics means rate of reaction. Rate or speed of the reaction. That is, a reaction may be thermodynamically feasible or stable, but it does not mean that it occurs very fast. It occurs very. They both are different things. Rate of reaction, that is kinetics, and thermodynamics. Thermodynamics will tell me whether a reaction is going to happen or not, whether it is at an unstable position and readily going to transform into a stable position. Kinetics, on the other hand, is going to tell me about the rate of reaction. How is this reaction going to proceed? It is going to proceed, no doubt. But at what rate, at what speed? In weathering, mostly the reactions are feasible, but the rate of reaction, the kinetics suggests that they are very, very slow. This kinetics is a factor of concentration. Obviously, if the concentration is more, rate of reaction is going to be more. I have more substance to weather, to react. It will definitely show me a greater rate. Second is surface area. Again, if the surface area is more, rate is going to be more. Because I have more surface area to react, the rate will increase. Third is temperature. Arrhenius equation suggests that for every increase of 10 degrees Celsius, 10 degrees Celsius temperature, the rate of reaction, chemical reaction doubles. So higher the temperature, more is the rate. Water is a great solvent. It basically dissolves and it increases the rate of reaction. So what it does is, water, first of all, it enters into the pore spaces and via multiple mechanisms, it disintegrates the rock. Another important aspect of water is what? Water splits into H plus, OH minus, and these are one of the great solvents. It increases the solubility and hence rate of reaction is increased. Also, if I'm talking about water, I must clear two things. Water moves in two directions. One is due to gravity. When it follows gravity, it basically dissolves soluble ions and leaches them away. Leaches them. This is another leaching. Another aspect of water is that water moves upward via capillary action. Capillary action. So what happens is that we will deal with capillary in the fluid dynamics, but what is the idea is that there is a capillary rise in the surface, in the entire surface, basically subsurface, there is a capillary rise. In soil pores, in the pores, we see water being, coming up a bit higher elevations. So this capillary rise is actually generating a very thin layer in the entire surface of the earth. So it is this surface where weathering is producing a lot of residue, a lot of physical and chemical weathering is going on at this surface. So this is very important. This layer is very important. All right. So we have seen that why does weathering occur? Why? We have talked about it. All right. So I have simultaneously given you the answer into two parts. That why does weathering takes place? Because of thermodynamics and kinetics. We have seen stability. We have talked about the structure. We have talked about the Goldilocks series. We have talked about the controlling factors, out of which concentration, temperature, surface area, water, and what else? Am I missing anything? That's all. So these are the primary causes of why weathering takes place. So in today's lecture, we have dealt with what is weathering, we have dealt with why does weathering takes place. In the upcoming lecture, we will see how weathering takes place. So I hope this is clear till here. Let us continue in the next lecture.